For the past 1 month, I've been working non-stop on this, building, testing, and recording every single episode of the Docker Home Lab series. It's not theory, it's 10 full practical Docker projects you can actually run on your own system. And today, I'm finally releasing the entire course repository on GitHub completely free. This repo includes all 10 episodes, each with its own folder, clear readme.md file, commands, and source code. You'll go from running your first container in episode 1 to deploying a real world stack with Flask, Postgres, and Nginx in episode 10. Everything you see in my videos, you can reproduce locally, step by step. Now, here's how it works. The GitHub repository gives you all the Docker source code and README files for free. But if you subscribe to my newsletter, you'll unlock interview questions, interview answers, labs that you can practice on your own, lab answers as well. It's the same for each and every episode until episode number 10. You'll have questions, answers, once again interview questions, interview answers, and 24 DevOps simulations I've been building over the last 5 months, covering Jenkins, Terraform, CI/CD, monitoring, and more. That's where you can really test yourself like you are working in a real company environment. Just head to this website. I'll put it in the description. Subscribe. It's completely free. You'll start getting weekly hands-on DevOps labs, answers, and real-world scenarios directly to your inbox. And if you are new here, hit subscribe on my channel Learn with DevOps Engineer. Every week, I drop 3 videos that teach you DevOps the practical way. Docker, Jenkins, Terraform, CI/CD, AI in DevOps. You can clearly see there are different playlists on my channel. Docker Home Lab series, DevOps Home Lab series, DevOps in Production Real World Simulation series, DevOps True Stories. So grab the GitHub repository, join the free newsletter, and start your Docker journey from episode 1. I am Arbaz from Learn with DevOps Engineer, helping you learn by doing. Let's dive straight into episode 1. Let me ask you this. What's faster, a virtual machine that takes minutes to boot up, or a Docker container which takes less than a second to start? In this video, I'll show you why Docker beats virtual machines, break down Docker concepts every DevOps engineer must master, and then we'll install Docker together and run our very first container. And here's the twist. At the end, I'll give you a sneak peek into a real world debugging simulation, the kind of problem you will see in production environment. So stick around till the end, because this isn't just a normal tutorial. This is a real world DevOps lab. If you want more hands-on DevOps content like this, hit subscribe right now and let's dive in. This is our virtual machine setup and this is our Docker setup. First, I am going to talk about virtual machine setup. So this is my hardware, my physical computer which I am using to record this video. In this, I will write it as PC. In this, we are installing an operating system. It can be anything: Windows, Linux, Mac, it can be anything. My PC has Windows operating system. On top of this, I am going to install a hypervisor. It can be VirtualBox or VMware Workstation or any other hypervisor you like. Then, once again, we are going to create virtual machine on top of this hypervisor. So this is, let's say, the guest OS of that particular virtual machine. Let's say Ubuntu. We are going to deploy application in this Ubuntu operating system. So this is the whole setup of this virtual machine. If I have to deploy an application, I need to follow this whole process. Let's talk about Docker now. So in Docker, this is my hardware, same exactly PC. And on top of this, I have my operating system, which is Windows. On top of Windows, I can install Docker and then launch containers. That would be these applications. So here I do not have lot of dependency. For example, here I have an operating system. Here I have hypervisor. Then followed by I have guest operating system. On top of this, I have application. In this Docker scenario, we are going to use the hardware and its host OS. Followed by we are going to install Docker and then run containers on top of this operating system. So the startup time here is very small when compared to a virtual machine, because on virtual machine the operating system image needs to start, whereas here we are using the host OS, so there is no need to install any kind of operating system. Normally we can directly run our containers. So that is the difference between a VM and Docker. I hope it is clear right now. I tried to explain in a very simple terms. Now let's jump into the Docker concepts. Now let's talk about Docker architecture and concepts. Let's talk about images first. So what exactly are images in Docker? An image is like a blueprint. It contains everything your application needs. For example, code, libraries, environments. If we pull Nginx latest image, I instantly get a ready to use web server. I don't need to do anything. I will just pull this image and run Docker container and my web server is ready. As simple as that. We are not going to install anything. We will just pull this image, run it locally. That's it. My job is done. Let's talk about containers. What exactly are containers? A container is a running instance of an image. For example, Nginx. One blueprint, unlimited running instances. That's why you can run 10 containers of the same application. For example, I will take Nginx image and I can run 10 containers isolated, each isolated from one another. Now let's talk about layers. What exactly are layers? Docker images are built in layers. If we make a small code change to our code, Docker doesn't rebuild everything. It reuses existing layers and only build the changed ones. That's why Docker builds are efficient. Now let's talk about registry. What exactly is registry? Images need a place to live. That place is called registry. Default is Docker Hub. There are some other registries as well. For example, AWS ECR or Azure Container Registry, or you can use JFrog Artifactory. I mean, there are like say so many different places that you can store these images. That is called a registry. Finally, we are going to talk about the architecture. What exactly is the architecture? Docker is a client server model. The Docker client is your CLI. From your machine, you are going to run Docker commands, or we can run Docker Compose as well. That talks to daemon, Docker daemon, also known as Docker D. The daemon handles the heavy lifting, as you can see in this image. It handles the heavy lifting, building the images, pulling from registries, running containers. They communicate via REST API, usually over a socket. Here's the cool part. You can run Docker client on your laptop and connect to a daemon running in a remote server. This is how DevOps teams manage containers across massive production clusters. All right, enough of theory and concepts. Now we are going to install Docker on a fresh virtual machine. I am going to use the virtual machine which we created in DevOps full course. By the way, if you are new to my channel and wondering how do I even create a virtual machine to practice Docker on, I got you covered. I already uploaded a full 2 hours DevOps course on this channel where we go step by step, starting with setting up a virtual machine, configuring Linux, networking, Git, Jenkins, and more. That's the perfect foundation before diving deep into Docker and Kubernetes. I'll leave the link in the description and cards. Check it out after this video. Now let's actually install Docker on a fresh Ubuntu virtual machine. First, we are going to run sudo apt-get update -y, which will update our system. Followed by, we are going to install some dependencies. Clear the screen, and then we are going to install some dependencies. This is done. Followed by, I'm going to create a directory called etc apt keyrings, and then we are going to download the official GPG key from docker.com. Then we are going to set up the repository using echo dbn command. Now once again we are going to update our system so that the new repository packages are available to install. Then we are going to actually install Docker engine. So I'm going to install Docker engine, Docker CLI, Docker Compose plugin. Docker got installed successfully. I did not come across any kind of errors. Now let me clear the screen and verify the Docker version. For that, I am going to run docker space --version. I can see Docker version 28.4.0 build is this. Now here comes the most interesting part. We are going to run our very first container. For that, I am going to say docker run Nginx. Press enter. Cannot connect to the Docker daemon at Unix is the Docker daemon running. First debugging process starts here. Now we need to check if Docker is running. Sudo systemctl status docker.service. Press enter. I can clearly see failed. Failed to start Docker service. Let me close this. Once again, clear the screen. Let's try to restart the service and see docker.service. Press enter. Once again, let's try to check the status. Yes, it works. And then now let's try to run our first Docker container. For that, I'm going to say Docker run Nginx. Press enter. I'm getting an error. Docker permission denied while trying to connect to Docker daemon. Okay, this looks like a permission issue, clear permission issue. So how do we need to solve this? If you are seeing any permission denied issue, first we need to make sure Docker group exists. For that, I'm going to run sudo group add docker. Press enter. I can see Docker group already exists. That means we need to add our current user to the Docker group. So I will say user mod -ag docker and $user. It will try to add my user, current user, to the Docker group. This step is important because by default, only root can access the Docker socket. Now for the changes to effect, we have two options. Either we are going to log out and log back in, or just run new group Docker. Now let's try to run our first container, Docker run Nginx. Press enter. So what exactly is happening right now? Behind the scenes, Docker client sends a request to the daemon. Docker checks if the image, Nginx image, presents locally. It says unable to find latest locally. Then it will try to pull the image from Docker hub. A new container is created and executed. Let's try to run our first container now. For that, I'm going to say Docker run hello world. Press enter. Here's what happens behind the scenes. Docker client sends a request to the daemon. Docker checks if the hello world image exists locally. If not, it will try to pull from the Docker hub. Exactly, if you see unable to find hello world locally, pulling from library hello world, followed by container got created, and we can see a message hello from Docker. This message shows that your installation appears to be working correctly. In this episode, we started by comparing Docker versus virtual machine. Then we broke down Docker core concepts like images, containers, layers, registries, and the client server model. Finally, we installed Docker and ran our first container. In the next episode, we'll Dockerize a real web application, deliberately break it, and debug why it isn't accessible. This is where you will see how Docker is used in real production debugging. If you found this useful, hit like and subscribe and turn on the bell icon so you don't miss the next simulation. Remember, this isn't theory, this is a DevOps lab. And by the end of this series, you will be thinking and troubleshooting like a real engineer. Thank you for watching and see you in the next video. In episode 1, we installed Docker, ran our very first container. But here's the truth. Real DevOps work doesn't stop there. Today, we'll take a real Flask web app, Dockerize it step by step, and run into 3 common mistakes that engineers make all the time. We'll debug it, each one, fix it, and make the Dockerfile production ready. Stick around till the end because These are the same mistakes I've seen break production pipelines at real companies. And if you are serious about becoming a DevOps engineer, hit subscribe right now, because in this series, we don't do theory, we do real world simulations. Now, before we jump into the demo, we are going to discuss about Dockerfile. Now, to run an application in Docker, we need a Dockerfile. What exactly is a Dockerfile? Think of it like a shell script. In Linux, we write shell scripts with a set of instructions to install packages, copy files, run some commands. So we are going to write all these steps in the shell script. A Docker file, a Docker file works the same way, but instead of automating tasks on your host machine, it's automating the process of building an image. Each instruction in Dockerfile, from, work directory, copy, run, cmd, is executed step by step like lines in a shell script. But here's the difference. A shell script directly runs on our laptop or server. If I give you my script, you still need the right operating system, libraries, and tools to work for it. A Docker file doesn't run commands, it freezes the entire environment, the base OS, libraries, dependencies, application in a portable image. So, if it works on my laptop, the exact same image will also work on your laptop, on AWS, Azure, or Kubernetes clusters. That's the power of Docker repeatability and portability. I'll write it down here: repeatability and portability. There are some prerequisites to make it work on every machine. For example, you should have Docker installed on your machine. That's, let's say, one of the prerequisites. All right, let's jump into the demo part, which is my favorite. So I have a Docker Flask episode. In this episode, I'm going to create some files. In the episode 2 folder, I'm going to create a file called application.py, followed by another file, requirements.txt file. Okay, then a Docker file. All these files are empty at the moment. I'm going to add some code to this. First, I'm going to add application.py code. It is a very simple Flask application where we are defining home, wherein we are trying to return hello from Docker, followed by host and the port. That's it. This is very simple. And then in the requirements.txt file, I'm going to add Flask is equal to 2.2.5 version. We need this particular version to make our application running in Docker. Followed by our main important topic of this video, Docker file. First and foremost, we are going to start with from. I'm going to say Python colon 3.10 hyphen slim image. I'm saying Docker to use this particular image. Followed by, we are going to say work directory would be application. Then we are going to say copy space dot dot. That means it will try to copy all the files in this particular folder. Then we are going to say run pip install -r requirements dot text file. So this step is kind of manually also you do when you are building Python applications. So it's the same step. I'm trying to add it in a Docker file. That's it, very simple. Then followed by command. So in general, if you have to run any application locally on your terminal, you will say Python comma the application name. Okay, the same steps I'm trying to write it in a Docker file. This is our first attempt. We are starting from Python 3.10 slim image, then set the working directory, copy the files, install the dependencies, and run the application. Save this. Now we are going to build this. Okay, let me open the terminal. Now let's try to build our first Docker image. I'm going to use my terminal and run this simple command. Docker build -t is tag Flask application version 1 space dot. Means I'm saying this command to check for a Docker file in this particular folder. So we should have this Docker file, then only this command will work. If you run outside of this folder, it will not work. I'm going to show you in a moment. Press enter. If you see, it is trying to build that Docker image. It will take a minute. So everything which we provided in our Docker file, it is using those instructions and trying to build it. And if you see, run pip install requirements.text, naming to Docker library app v1. I'm going to clear the screen. As promised, now I am going to build the Docker image from the episode 1 folder. Let's try to run the same command and see what will happen. Press enter. If you see, I don't have any files in this particular folder. Now let me try to run this command once again and see what exactly will happen. Docker build -t Flask application version 2 space dot. Press enter. I see the error, failed to solve, failed to read Docker file, open Docker file, no such file or directory. So without Docker file, you cannot build images. This is kind of mandatory step. That's why it passed in our second episode folder. Let me clear the screen. If you see, we have this Docker file, the same file. That's why we were able to build the image successfully. Now let's try to run our first Docker container. For that, I'm going to run Docker command. Docker run -d means in detached mode -name Flask -v1 using this particular image which we built, Flask -app v1. Press enter. Now let me try to list that using Docker ps. I can see container is up and running. Now let's jump back to the browser, open the tab and paste localhost 5000. This site can't be reached. This is exactly the kind of situations you'll face in real projects. Let's debug. Our Docker container is running fine, but we cannot access the container. Let me clear the screen. Now let's try to check out from the terminal. I'm going to run curl command http://localhost 5000. Press enter. It says failed to connect to localhost port 5000. Connection refused. We are going to run docker port Flask -v1. Press enter to check if the port is exposed correctly. I do not see any output That means we did not pass the port. So let's do that real quick. We use docker-d name flask v1 flask app image name. We actually forgot to add port 5000 colon 5000. We need to add this port. Before doing that, let's try to stop our Docker container. Before, let's try to stop our Docker container. Docker stop the container name. Press enter. Now let's try to publish port so that we can access the container from localhost. Space, press enter. I get another error now. Error response from Docker daemon. The container already exists. I need to remove this. So I'm going to say docker rm space the container name. This is done. Once again, let me run docker run container command. Now I can see the container ID once again. Docker ps, the container is running. You see, previously we were not seeing this, publishing at particular port. Now hopefully we should be able to access. I'm going to reload this page. Wow, congratulations. Hello from Docker. This works out of the box. We forgot to publish the port, and also now this brings me back to the second mistake, expose 5000. Docker knows this app listens on port 5000. Expose doesn't publish the port by itself, but it documents it. In local runs, we fix this with -p, but in real world setups like Docker Compose, Kubernetes, or Swarm, missing expose can break automation in subtle ways. Now let's talk about the third mistake. If you look at this Docker file, everything looked fine. We were able to build it, and also we were able to run it successfully. But if you see it here, I tried to copy everything before installing dependencies. That breaks caching. If I change even one line of code, Docker will rebuild all dependencies from scratch. In CI/CD pipelines, that waste hours. The best practice is we are going to remove this from here, and I am going to paste this under the pip install -requirement.txt. And here we are going to copy only requirements.txt file. That's it. I'm going to save this file. If you look at the folder structure, we are missing one file .docker ignore. It is exactly like .git ignore. We need this file mandatory because there is a high possibility that you are going to copy everything. Sometimes you will have .env files as well, which will get copied to Docker image. If you add, all these files will be exempted to build our Docker image. I'm going to clear the screen. Let me stop Docker container real quick, and also I will show you the difference. Docker stop, enter. Now let's try to rebuild our Docker image. I'm going to use version 2 space dot, press enter. So we are rebuilding our Docker image. Now once again we are going to run this Docker container using the version 2 which we built. Press enter. Our container is like running. Let me do Docker ps quickly. Yes, I'm going to refresh the page. Hello from Docker. We have successfully built our Docker image. Quick recap of what we learned today. Always copy requirement.txt First, to use caching, always publish ports with -p and add expose for clarity and orchestration tools. Always use .docker ignore to keep images lean. And always tag your images properly. Never rely on latest in production. In this episode, we dockerized a real Flask application and we hit many mistakes. Bad copy, missing port, images without .docker ignore. All these aren't toy problems. I've seen all of these caused outages, broken pipelines in production environment. In the next episode, we are going one level deeper. We'll connect the application to a database inside running Docker container, deliberately break the networking, and debug why that application can't reach the database. That's exactly the kind of issues you'll face in real world DevOps jobs. If this video helped you, smash that like button, hit subscribe, and drop a comment. What's the biggest mistake you made in a Docker file? Let's learn from each other. Remember, this isn't just Docker practice, this is a real world DevOps lab. And by the end of this series, you'll think and debug like a production engineer. Thank you for watching and see you in the next video. I just ran Flask application inside Docker and my Postgres database is running too. Let's look at the browser. If I look at the browser, I see an error saying connection to server at localhost failed. This is one of the most common mistakes engineers make when running multiple container applications. In this episode, we will break it, debug it, and fix it step by step. Before we dive in, if you want to master DevOps through real world simulations like this, hit subscribe right now. On this channel, we don't do theory, we do real world debugging. You don't want to miss the next episode. Here's the root cause. Let me draw two quick boxes. One is Flask container and the second one is database, Postgres database container. And from this container to this container, it is trying to connect using localhost. Means inside Docker, each container has its own localhost. So when Flask connects to localhost, it is trying to point to itself, not Postgres database. That's why it fails. In my DevOps full course video, I showed you the difference between NAT network versus bridge network. NAT keeps the VM isolated. It's like Docker's default network. Whereas bridge network lets the VM share the host network, just like Docker's user defined bridge network. If you haven't watched my full DevOps course, I explained NAT versus bridge networking in detail there. That's the perfect foundation before Docker and Kubernetes. Check it out after this video. Now let's jump into the demo. First, I'm going to run the database. Here I'm running Postgres in Docker, setting up username, password, and database. This is a real Postgres database isolated in its own container. Press enter. The database is running. So let's look at the application code. In this episode 3 folder, I have application.py, Dockerfile, requirements.txt, environment file. First, I'm going to start with application. This Flask application connects to a Postgres database, but here's the problem. Host is equal to local host. On my laptop, that works fine. Inside Docker, local host means the container itself, not the database. So this one line guarantees our application will fail. Now look at the Docker file. It's the same exact Docker file we are trying to use from Python. Working directory is application, copy requirement.txt, then run pip install no cache directory -r requirements.txt, followed by copy, then expose, then we are trying to run the application. It's the same exact steps which we did in our previous episode. In requirements.txt, we are adding another dependency that we are trying to install, and I have .env file. In production environments, we are not going to hard code on our terminal. Locally, you can do it on your machine as I did here, but in production environments, this is not the right way, the command line. We need to use .env files, pass values there. I'll show you. I'll try to show you how we are going to run this now. Also, we need to add .docker ignore. If you see, I tried to add .env file as well. My credentials are not getting copied to the image itself. So now we are going to build Flask application. I'm going to use version 5 space dot, press enter. So it will try to build the application. Then we are going to run that real quick. So for that, I'm going to say docker run all these commands are like the same commands which I used in my previous video. So I'm not explaining once again. Docker run -d name Flask. I'm just changing the version here. And also Flask application -v5 would be the name. Press enter. Now our both containers are running. Now let's try to list the containers. So I can see Flask application v5 is running and also our Postgres is running. The containers started successfully. If I jump to the browser and refresh, I see connection to server at localhost port 5432 failure. Flask is trying to connect to Postgres at localhost port 5432 and it fails. That's because localhost here points back to the Flask container. As I showed you, if you look here, we are trying to point it back to our local host. That's because local host here only points back to the Flask container. The database is in a completely separate container. Now let's try to stop that real quick. Docker stop the container name. The same for Docker stop container name. And then we are going to remove this as well. Flask-app -v5 docker rmi docker rm followed by I am going to remove docker rm flask db. Press enter. Now let's try to create a network. For that I am going to run docker network create flask-net. Press enter. Docker network ls will give you a Flask network. Okay, it's a bridge network as you can see. Now I'm going to update this localhost with flask-db and save. Then we are going to rebuild the application. Docker build command followed by version 6 would be, let's say, the latest version. We have successfully built our Docker image. Now let's try to run the database once again. For that, I am going to use flask-db as the name, followed by the network which we created, flasknet, and environment file. If you see from my previous step, I did not hardcode my username password. I am trying to pass this .env file so that my username and password are safe. Postgres database. Press enter. The container started, followed by the next container, that is our Flask application itself. I'm going to use Docker run the same. The only flag we are adding here is flask-network. Let me change the version real quick. That is 6. Then 6 here as well. Press enter. Now let me clear the screen. Docker ps. Our both containers are running. Let me go back to my browser and try to refresh. And here we are. Hello from Flask plus Postgres. What did we do? We created a user-defined network and connected both containers to that particular network. Now, instead of localhost, Flask connects to the Flask database. Docker's internal DNS resolve container names. Let's do a quick recap of what we learned today. Flask and Postgres were running in separate containers. Each container had its own local host, so Flask couldn't see Postgres. The fix was creating a Docker network and using the container name FlaskDB instead of localhost. In this episode, we broke Flask plus Postgres networking, saw why localhost fails, and fixed it with Docker networks. In the next episode, we are going to simplify everything with Docker Compose, manage multiple containers with just one file. And yes, we are going to break that too. So you learn how to debug Compose like a pro. If this helped you, hit like, subscribe, and drop a comment. What's the trickiest networking issue you faced in the Docker? Thank you for watching and see you in the next video. One wrong command, docker rm-f flaskdb, and my entire Postgres DB is gone. This is the mistake that burns people working with Docker every day. Containers are ephemeral, which means if you delete them, all the data inside that database is gone. In this episode, I'll show you how to persist data with volumes, break it on purpose using a wrong bind mount, and then fix it right away. Stick till the end because losing production data is the last mistake you want to make as a DevOps engineer. If you are serious about learning Docker through real world simulations like this, hit subscribe right now. Every week we break things on purpose so you learn how to debug them like a pro. Before jumping into the demo, I would like to give you a small explanation. Here's what's exactly happening. Let me draw a quick container, small container. A container file system lives inside the container layer. When you delete the container with docker rm command, the writable layer disappears. That's why the data from our Postgres database is gone. To fix this, Docker gives us two options. Number one is named volumes managed by Docker, safe and reliable for databases. The second option is bind mounts, meaning we are going to map a folder which is on our host PC. Second option is flexible but risky if you point it to the wrong folder path. Now, the official Docker documentation goes into TMPFS mounts, storage, drivers, and more. We will keep it practical for real world DevOps. What matters is this: using number one, named volumes for databases, and the second option, we have to be careful with bind mounts. Now let's jump into the demo. So I'm back into my Visual Studio Code. So in this folder, I have episode 4 persistent volume. Here I have commands.sh file. So I'm going to follow one by one command, and I'll also try to explain you. We are going to run database without volume. For this, I'm going to use this command docker run -d. Name would be db1, Postgres user, Postgres password, and the db name. Press enter. Our database is running. Followed by, we are going to insert some data into this database. I'm using docker execute command. -it is like interactive mode. db1 is like our container name. And I'm using plsql command here to create table if not exists. I'm going to create test table. Integer would be primary key and insert some values. Okay, press enter. I can see that insert 0 1, we inserted some data. Now let me quickly restart this container. So for that, I'm going to use the container ID followed by docker restart the container. Press enter. So I did restart the container. Let's try to run another plsql command. Select star from test. Press enter. So I can see some data. Restart did not affect anything with respect to data. Now I am going to remove that particular container. So I'm going to copy the container ID. Then I would say docker stop container followed by docker rm container ID. Then if I try to run the same command once again, I get error response from daemon. No such container db1. So let me start the container once again. So I will use the same command. I'm going to rerun the container once again. Press enter. If we check that command, I get an error saying relation test does not exist. That means our data is gone because we are not using volumes. Now let's try to create some volumes. So for that, I'm going to use docker volume create followed by the name pg data. Press enter. Now we have the volume created. Now let me run the docker container command once again. For that, I'm using the docker run. For that, I'm using docker run -d in detached mode, and the name I'm giving it as database2. The same credentials, username, password, and the db name. Here, if you see, we are trying to add volume. Volume is, let's say, a flag, and the volume which we created, pg data. Also, within the container, we are saying to point out this data in this particular location. Okay, press enter. Now my container is running once again. Now let's try to insert data once again. Now let's try to insert data into the db2 database which we created. So I'm using once again the same command, docker execute db2 psql -u demo create table if not exists test insert into test values 2. Press enter. I did inserted. Now let me do docker ps. I'm going to copy this container ID and then say docker stop container ID followed by docker rm space container ID. Let me list that. My db3 is gone now. So I need to rerun the container. So I'm going to use the same command once again. Copy and paste it here. Enter. My container is once again running. Followed by, now I'm not going to insert any data. Let's try to check if we can access this data. Okay. Press enter. If you see, I did not insert any new data because we had volumes. In spite of removing the container, we can still access the data because we are using volumes here, PG data. That's the power of named volumes. They persist data independently of containers. Now let's run another simulation. In this case, I'm going to run DB3 now, database. And in terms of volume, previously we used PG data. Now I am trying to use temp folder wrong path. I am trying to bind the mount path. For example, in this case, temp wrong path. Press enter. If you see, my container is, let's say, running. And let's try to insert some data. Let me copy this command real quick. And then I'm going to say db3 here. Rest all would be the same. Press enter. Let me real quick look at the container. So I'm going to copy the container ID, clear the screen, docker stop container ID, press enter, docker rm container ID, press enter. Now let's try to rerun the container using the same command. Followed by, I'm going to execute select star from command to check if we can see the data. My data is still there. Now let's try to run the Docker container once again using the wrong bind mount. That means I am going to give my own data directory instead of volumes. I am going to pass the data directory from my local host machine, and let me try to run this real quick. So previously we created this volume path, for example PG data. Now I am directly passing this particular path instead of creating the volume. Let's do that real quick. Press enter. So I did create this, followed by, let me insert some data real quick. So for that, I'm going to use the same command once again, docker execute, followed by, I would say db3 here. Press enter. We have some data here. Let's try to search that data real quick. And I'm going to say db3 once again here. I can see some data here. Now once again, I'm going to rerun this container using the same docker run command. Instead of db-data, I'm going to use db data. Okay. Manual mistakes are mandatory. It might happen for some or the other reason, but that's for sure. Now let's try to rerun the docker db3 container. If you look at the volume, previously we had temp db-data. Now I'm going to remove this hyphen and try to start this container. For some or the other reasons, we have to restart the container, and a developer is playing around with this stuff. And he tries to restart the container. Container started successfully. Now, if we look at the data, I'm going to execute real quick. If we look at the data, select star from test, the data is gone. Why? Because you are using the wrong path. And you will be in a panic situation. This is the danger of bind mounts. One wrong folder and your database won't even start. This is the danger of this particular volumes if we give our own host path. DB data, it will try to recreate the new database and we cannot even find our data which we inserted or created in previous steps. Now let's try to quickly fix that issue. I'm going to say docker rm-db3 followed by we are going to use pg data. Once again pg data, press enter. Now if we look at the select statement in the db3, I can see the data is still present. The fix here is going back to named volumes. They are managed by Docker, portable, and much safer than bind mounts for database. Let's do a quick recap of today's episode. Containers are ephemerals. If you delete them, data is gone. Named volumes are the best way to persist databases in Docker. Bind mounts are powerful but dangerous if you mount the wrong path, as we have seen in the demo. For 90% of real world setups, just stick with named volumes. In the next episode, we will deal with a very different failure, a container that refuses to stay alive. You will see how to debug a container stuck in a crash loop using Docker logs and Docker execute. If this helped you, hit that like button, subscribe to my channel, and drop a comment. Have you ever lost data in Docker because of missing volumes? Thank you for watching and see you in the next video. I just started my application container and it refuses to stay alive. Look, it runs for a few seconds, it dies, and it starts again, over and over again. This endless cycle is called a crash loop. In this episode, I'll deliberately break a container, walk you through every step of debugging it with Docker commands, and then fix it. Stick around because these are the kind of issues that appear in production environments every day. And knowing how to debug them makes you a real DevOps engineer. If you are serious about Docker and DevOps, hit subscribe right now. On this channel, we don't just install tools, we simulate real failures. So you are prepared when they happen at work. Let's talk about what exactly happening before we jump into the demo. First, let me write down something. Start followed by crash, then restart policy, then loop. Docker starts the container, application fails inside, so we are seeing the crash. Because of this restart policy, Docker tries to bring the container back online. But the bug is still there. It fails again. We are stuck in a loop. The container will try to start, application crash, restart policy will bring Docker container back up again. Again it fails. It's the same process. It's a never-ending loop. In Kubernetes, this shows up as crash loop back off. In plain Docker, you will see it as a container stuck in restart mode. Now let's jump into the demo. Here I have episode 5 crash loop folder. In this folder I have application.py, Dockerfile, and requirements.txt. So let's start with application.py. So this is very simple code. It expects an environment variable. If this is not set, Python raises a error and the container dies immediately. So first we are going to start by building the image. For that I'm going to say docker build -t crash application v1 space dot. Press enter. So as soon as we build the image, we are going to run that container using the same image. Let's try to run the container using the image which we built just now, crash app v1. I'm running the docker run command followed by the name is crash1. Always I'm trying to pass this flag so that I don't want to restart containers manually. -p port 5000 crash app v1. Press enter. Container started. Let's look at the container. So now let's look at the running container. For that I'm using watch-n command. 2 seconds is, let's say, the time period to refresh every 2 seconds and run this particular command. Docker ps -n filter name is equal to crash1. Press enter. If you look here, container id crash app v1 is the image, python app.py 45 seconds ago, restarting in 17 seconds ago. You will see this message. Crash1 is, let's say, the name. So if we wait for a few more seconds, it will try to restart. Restarting 1 second ago. Container got stuck in a loop and it keeps on failing. Let me control C. Let's try to run docker inspect crash one pipe grep -i restart. Press enter. So I can see the status is restarting. Restart count 11. Restart policy. Now let's try to get into the container. Docker execute -it interactive mode crash1 and environment variables. Yes, I get an error saying error from response from daemon. Container is restarting. Okay. If the container is in restart mode, I cannot even connect to the container. So docker execute doesn't even work. The container dies before we can get inside. This is what makes crash loops so tricky. You can't just open a shell and poke around. Now here comes our savior. Docker logs crash1. Press enter. If you look at here, I can see a clear error saying key error app secret. Okay. With this, I get an idea. Okay, something is wrong with our application code. Line 4, if you see app.py, line 4, os.environment app underscore secret. So if we go back here the line 4, it says apps underscore secret. The app is crashing because the environment variable isn't set. Now let me clear the screen. Now let's try to stop the container, and also let's try to remove that container so that we can restart it once again. Now let's try to fix that issue. I'm going to run the container once again, but if you look at here, I'm trying to pass the app secret here. That means our container should start normally without getting restarted. Press enter. Let's try to run the watch command once again. Press enter. If you see here, up 14 seconds ago. That means container is, let's say, starting up. It's not going to the restart or loop back stage. Let me jump back to my browser and try to refresh it here. Yes, app is running. Secret is equal to super secret. We just added one environment variable called super secret and our application is running. The application starts, stays up, and the crash loop is gone. Debugging complete. This is how you try to debug in real world production environments. Let's do a quick recap of this particular episode. A crash loop happens when a container starts, fails, and restarts endlessly. Always use Docker logs first. It usually tells you the exact problem. Docker inspect helps you confirm restart policies, as we have seen in the demo. You can't always execute into a crashing loop container, so logs are critical. The fix depends on the root cause. In our case, it was a missing environment variable, whereas in other cases, it can be a different issue, but the process is same. In the next episode, we will move back to Docker Compose. We'll run a full stack application, Flask, Postgres, Nginx, and I'll break it with a bad YAML configuration so you learn how to debug compose errors. Don't miss it. Hit like, subscribe, and comment if you ever seen a container stuck in a crash loop. Thank you for watching and see you in the next video. Imagine this. You got a web application, a database, and a reverse proxy. Do you really want to type 3 different Docker run commands, wire up networking manually, pass all the environment variables by hand every single time? That's painful and in production impossible. In this episode, I'll show you how Docker Compose solves this problem. One file, one command, and your entire stack is up. Stick around till the end because we will even break it on purpose with a bad configuration so you see how real debugging works. If you want more real world DevOps labs like this, hit subscribe right now. On this channel, we don't install tools, we build and break real systems. Here's our architecture: Web, DB, Nginx, reverse proxy, Flask application for the backend, Postgres for data, Nginx as a reverse proxy. Instead of managing all 3 containers separately, Docker Compose runs them in a single network with one YAML file. Let's jump into our Visual Studio Code. Here I have episode 6, Docker Compose. I'm going to open this particular folder. In this folder, I have Flask application folder. It consists of my application.py, Dockerfile, requirements.txt. And on the root folder, I have docker compose.yaml, which we are going to write in a moment. Nginx.configuration. So let me start from here. I already explained about this particular application in my previous episodes. Here we are using Flask application. It's a very simple application. We are trying to connect to the database using db host, db name, db user, and db pass. And we are trying to display this particular message. If everything works successfully, we should see this message in our browser. Now let's look at the Docker file. So Docker file is also almost same. From Python, work directory is like application directory, copy requirements.txt, run pip install, copy, then expose 5000, cmd, run this particular application using Python. It's the exact same steps which we are following across the series. If you are new to my channel, please go and watch my other episodes as well. Followed by requirements.txt. We are trying to install these dependencies. Then docker compose.yaml. Let me start from here. First, we have 3 different services. So I would say services, followed by first service is web, which is our Flask application. Then we are going to build using .flask application. So in this line, we are saying to build from Docker file inside Flask application folder. So if you see my Flask application folder, we are going to use this particular Docker file and we are saying to build this Flask application. Map ports, in this case, that would be 8080 to 5000 port, followed by environments. That would be app secret is equal to super secret, then db host, it is the same exact stuff which we have in our application code, then followed by db name, that is equal to flask db, then db user, that would be flask user, db pass, that would be once again flask pass, followed by we are going to write depends on, because I would like to start this after my database is up and running. Now let's jump into our next service, that would be database, followed by image name. So I am trying to take the public image here, Postgres 14, then environments, exact same steps we need to follow. Environments here would be Postgres user, that would be Flask user, Postgres password, Flask pass, then Postgres db, that will be Flask db. Press enter, and then we are going to add volumes. In our last episode we already discussed about volumes. If you haven't checked out, please go and check that as well. Var lib postgres ql/data. Here named volumes we are trying to define here. Now let's write our Nginx service. So for the Nginx service, we are going to give image as Nginx. It's a public image, Alpine. Then followed by ports. We are exposing ports here. So that would be 8080. Then we are going to add volumes as well. We are going to add our own mount file. So in this case, I'm going to add Nginx config from our local to the container. So let me write that real quick. So in the container, the path would be Nginx/Nginx dot config colon read only permissions I'm trying to give here, followed by depends on. So it depends on web, so we need to add that. It is going to start after the web. In the end, we are going to add volumes, db data. We are declaring named volumes here. One file, three different services. Database has persistence. Flask knows db host is just db, no IP is needed. Nginx proxies traffic to web, and compose automatically creates a network. We are not creating any network manually here. Now let's look at our Nginx config. Nothing fancy, just proxying request to the web service on port 5000. Notice we are not using local host, instead web, because inside compose services talk by name. Now let's try to run docker compose and see if our containers will start. Docker compose up, press enter. I see the first error, validating services.web.depends on .db must be a mapping. Let's see what's going on. So services.web.depends on.db. Okay, I think I did a mistake. I need to write something like this. So let me try to run once again. Docker compose up services.db additional property environments is not allowed. Yes, I can see another mistake. Spelling mistake. Environments save. Then let's try to do docker compose up once again. Environments. Okay, environments is not allowed. It's a typo here. Let me clear the screen and then let's do it once again. Docker compose up, press enter. Same here, let me copy paste that. Docker compose up, press enter. So if you see, networking created, volume is getting created, container db1, web1, nginx1. If you see, we are creating 5 different stuff here. If you do the same manually, I need to open 4 different terminals. Like, it would be very difficult in production environments. So let's scroll down and see if everything looks good. So far, good enough. Let me open the browser real quick. Yes, error could not translate hostname db to address name or service not known. Okay, I see some problem here. So looks like our database did not start. Error, database is uninitialized and super user password is not specified. Okay, so looks like our database did not start, but I did pass a password here. Let's try to update exactly as it is shown here. So I'm going to paste it here, save it and close that. Restart everything once again. So I will just say docker compose down. So it will remove all my containers. Clear the screen. Docker compose up. Press enter. Now let's see what's going on. I will not go to my browser. Here I can see exactly what's going on. So network created, db1, web1, nginx1 created. Volumes we did not delete completely, that's why it did not create. So looks good so far. And also I can see database is ready to accept connections. All right, so let's jump into the browser. Let me refresh it. I can see a different error now. Error, connection to server at db, port 5432 failed, fatal, database does not exist, Flask db does not exist. Now let's try to debug using logs. For that I'm going to first check the container name, docker compose ps. I will try to copy this, followed by I would say docker logs and the container name. Press enter. So here in this log we'll come to know what exactly is happening. So if we read through what's going on, I can see the error message here. Database Flask db does not exist. So let's look at the web application. So the problem is from web to the database. So in the web, I have environment variables. DB name is Flask DB here. I'm going to copy this. This looks good. Whereas if I go to DB, here I can see Flax. Okay, FLAKS. It's a typo. I need to update that real quick. After updating, now let's try to close this. We try to update our Flask DB here and restart our Docker Compose once again. So I would say Docker compose down, and then Docker compose down -v to remove volumes as well. I would say Docker compose up once again, and let's see if it will work now. So I did start my Docker compose. Let's jump back to our browser, refresh, and here we are. Hello from Flask plus Postgres via Docker compose. If you are new to my channel, hit subscribe right now so you don't miss the next episode. So finally we were able to solve the mistake. Now let's do another mistake. So let me close this real quick. So I'm going to update the Nginx config. Instead of web, I would say localhost. What do you think will happen now? Docker compose up, press enter. Let's see if we can access now. So I'm going to go back to my browser and try to refresh the page. I get 502 bad gateway. Okay, because we updated the proxy path. It is pointing out to itself. Localhost 5000. It's not going anywhere. As I said, containers will have their own local host. So if you give localhost, it will get confused. So I'm going to remove this and add web back, close it. And also if you see, we can see the error here. Connection refused while connecting to upstream client server upstream localhost 5000. So it will not work. So let me refresh this 502 bad gateway. And then now let's try to do Docker compose up once again. Hello from Flask plus Postgres via Docker compose. If you are new to my channel, hit subscribe right now so you don't miss the next episode. Debugging in compose is the same as Docker logs and execute. But the nice part is you can run them per service, not container IDs. For example, I did run Docker logs, episode 6, Docker compose db-1. So I can see the logs here. Also, the same way I can go to another service. So for example, I would say Docker logs and the service name. Press enter. So I will get the logs of that particular service. So the same way you can check for all the services. Let's do a quick recap of what we did today. Compose replaces messy Docker commands with one YAML file. It handles networking automatically. We did not create any networking manually. Also, YAML indentation errors and wrong services are common mistakes. Debugging works the same, logs and execute, same like Docker logs the service name. It is the same with Docker Compose as well. In the next episode, we will learn how to build optimized Docker images using multi-stage builds. I'll show you how to shrink image size in half and what happens if you forget .docker ignore and ship a 1 gigabyte monster image by mistake. Hit like, subscribe, and let's keep breaking things together. Thank you for watching and see you in the next video. Take a look at this. Two images, same application. One is a monster 2.29 gigabytes. The other is just 134 MB. Imagine which one you would want in your CI/CD pipeline. In this episode, I'll show you exactly how I created this bloated image and how we shrink it down using multi-stage builds. Stick with me. By the end, you will know how to build fast production ready images like a real DevOps engineer. If you are new here, hit subscribe right now. Every week, we don't just run Docker, we break it, optimize it, and debug it, just like you will have to in production environment. In a naive Docker file, you start with a heavy base image, then install way too many dependencies and copy unnecessary files. That's how you end up with 2+ GB of image. In a slim multi-stage build, you only keep what's needed to run the application. Result, a tiny and efficient image. Now let's jump into the demo. So here's my episode 7 image optimization folder. In this folder, I have multiple files: Docker ignore, application.py, Dockerfile bloated, Dockerfile optimized, requirements.txt. We are going to start with Dockerfile bloated version. So if you look here, we are starting with Python 3.10 with big base image with lots of extras, followed by working directories like application directory. Then we are going to copy everything. I do not even have .docker ignore here. Followed by installing. We are trying to install compilers, JDK, Node, Yarn, React CLI plus heavy Python libraries. Most of this is not needed in production environment. Followed by exposing our port and just run our application. So we just installed a full development environment inside our image. That's why it explodes past 2 GB. Let's try to build that real quick. I'm going to build that image now with docker build -t flask fat name with a version 1 tag and the Dockerfile bloated. Press enter. And here it is. Slow to build, slow to push, slow to deploy. This is what happens when you don't optimize. It will take a lot of time. It depends on the speed, network bandwidth and all. I'm going to wait. Till then, let's discuss about Dockerfile optimized version. So we start with our builder stage. Notice I'm using Python 3.10-slim, not the full Python 3.10. The slim image strips out unnecessary system tools, make it smaller and faster to pull. I also give this stage a name builder. That way I can reference it later. Working directory. This means all future commands run inside application directory. Standardizing the working directory keeps everything clean and predictable. Here's the key. In the builder stage, I install temporary build dependencies like build essentials, GCC. These are needed only for compiling certain Python libraries. But notice, immediately we are trying to clean up. That removes the apt cache, preventing extra MB from sneaking into the image. This is a best practice. Install what you need and clean up right away. Next, I copy in only the requirements.txt file. This is important because Docker caches layer. If I copy all the code first, any change would break the cache and force pip to reinstall everything. By copying just this file, I only trigger reinstall when dependencies change. Then I run pip install --user no cache directory. User means install packages in the user directory, not system wide. No cache directory avoids keeping pip's cache which saves disk space. Final copy. I copy the rest of the application code. This happens after dependencies, so code changes don't invalidate pip cache layers unnecessarily. Again, It's all about faster builds and smaller layers. Now for the second stage, runner, I start with fresh from a clean Python Slim image. This stage has no compilers, no build tools, nothing unnecessary. It's production ready. Same as before, working directory. First, I copy the installed Python packages from the builder stage. Then I copy the actual code. Notice how we don't compile apt tools or caches, just the dependencies and code. This is why the final image is so small. This line updates the path so that the installed Python packages are available. Without this, pip installed user packages wouldn't be found. This ensures Flask and other dependencies can run correctly inside the container. Finally, I expose port 5000, the default Flask port, and set the command to run the application clean, minimal, and production ready. Now let's try to build our Slim image. For that, I'm going to run docker build flask -slim. v1, I'm going to use Dockerfile optimized here. Press enter. Let's start with the fat image. Press enter. If you see this, I can see my fat image got built successfully, but the size is 2.29 gigabytes. That's how big it is. Now let's look at our slim image. Press enter. 134 MB. You see the difference? 2.29 gigabytes, 134 MB. If you look at our bloated file, I have around 25 lines of code and it gave me 2.29 gigabytes of file, whereas optimized also has around same 26 lines of code and I got 134 MB. Now let's try to inspect the layers. For example, Docker history. Docker history will show you the layers. V1, if you look at the layers, here I can see 120 MB, 60.2 MB, 656 MB, followed by I can see 1.2 gigabytes here. Okay, this particular layer is taking 1.2 gigabytes. Let's look at our slim image history. I'm going to clear the screen. Press enter. So if you see here, everything is in MB. I don't see anything like gigabyte here because we wrote production ready multi-stage build Dockerfile. You might be thinking, why am I stressing so much about this size? In real production environment, smaller images is equal to faster CI/CD pipelines. Okay, this is one of the most important point you need to remember. Less network transfer is equal to cheaper bandwidth, followed by smaller attack surface is equal to better security. And imagine debugging a crash with a 2 gigabytes pull versus a 134 MB pull. Which one would you rather deal with? Comment below. Now let's do a quick recap of today's episode. A bloated Docker file with a fat base image plus unnecessary tools is equal to 2.29 gigabytes monster. Multi-stage builds let you separate build dependencies from runtime. Slim base image plus .docker ignore plus copying only what you need is equal to production ready images. In the next episode, we will talk about container security and permissions. You will see why running as root inside a container is dangerous, and we'll break an application with permission errors to learn how to fix it. Hit like, smash subscribe, and don't miss it. Thank you for watching and see you in the next video. Look at this. I just ran a container and I typed who am I, it says root. That means this container has full power over its file system. It can bind to any port, and if it somehow escapes, it could affect the host system. In this episode, we will see why running as root is dangerous, how to run containers as non-root, and debug a real permission issue that happens in production. If you are new here, hit subscribe right now. Every week we simulate real DevOps mistakes so you can debug them like a pro. Let me draw two boxes. One box is a default container and the second one is a non-root container. It has a root user, it has a particular user. If an attacker escapes from this container, it can access our host PC. In this, it's like a restricted user, so it cannot do anything. So containers don't magically remove root risk. By default, processes run as root. If an attacker escapes the container through a kernel exploit or a misconfigured mount like var run/docker.sock, they can easily become root on our host PC because containers are directly running on our host PC, not in a virtual machine. Best practice, always run as a dedicated user inside the container with only the permissions they need. Let's jump into the demo. Let's try to run this container and get into that container. So for that I'm using docker run and the flask-non-secure bash, press enter. So right now I'm inside this container. I will write who am I. So you can clearly see that I'm a root user. So in this user, I'm going to create a file, touch /root secret.txt. Press enter. Now let's go to that location and see if the file got created. ls, you can clearly see that secret.txt is here. Also, let's try to update some packages here. Sudo apt-get update, press enter. Inside this container, I am root. I can update packages, create files in /root, basically do anything. In production, that's dangerous because if I escape the container, I'd still be root on the host machine. Now let me exit from this. So this is our episode 8 folder. I have different files: application.py, Dockerfile, Dockerfile v2, v3, requirements.txt. Now let's jump into our Docker file. So this is the same exact Docker file from our previous episodes. If you are following along, you should be familiar with this particular Docker file which I am showing right now. I am trying to create application user. I am running this command run user add -m application user, followed by, after copying all the directories, I am trying to tell user application user. So I'm telling it should run as application user. Now let's try to build this. Now let's try to build our Docker file. So docker build flask-secure v1, press enter. Our Docker image got built successfully. Once again, we are going to run the Flask secure container. Previously it was non-secure, now secure one. Bash, press enter. Right now I'm into the container. If I write who am I, you see application user. Now let's try to create a file in root location. Touch /root /secret.txt. Press enter. Permission denied because we are running as application user. And also let's try to do apt-get update. Press enter. It says could not lock, permission denied. You see the difference now between the root user and application user? That's how it is. Now let me exit from this. Now let's look at the version 2 Dockerfile. Here we are trying to add user and also use that particular user. Instead of exposing 5000 port, we are exposing port 80. And in my application code as well, I changed it to port 80. Let's try to build this and see what will happen. I'm using the docker build command, Flask secure version 2, Dockerfile v2. Dockerfile v2. Press enter. Once this is built, we are going to run this using our port 8080. Docker gives containers some extra kernel permissions called capabilities. One of them is netbind service, which allows this to work. In hardened production environments, those capabilities are usually dropped, and that's when you will suddenly hit permission denied errors after switching to non-root user. The safer and more portable fix is simple. Don't use privileged ports at all. Change your application to run on a higher port like 8080. For example, here instead of 80, I'm going to use 8080. And in my Docker file as well, I'm going to expose it as 8080. Okay. Let me try to build this real quick. So I'm using docker build command once again, Flask secure version 3, followed by here this would be version 3. Press enter. Now let's try to run our container once again using port 8080, Flask secure version 3. Press enter. So if you see, it is perfectly running on our port 8080. Let's do a quick recap of what we learned today. Don't run as root inside Docker containers. By default, Docker runs as root, and we saw why that's a risk. Always create a dedicated application user. Use non-privileged ports like 8080 or 5000. Drop Linux capabilities unless you explicitly need them. And scan your containers with tools like Docker Bench for security issues. In the next episode, we'll integrate Docker into a CI/CD pipeline with Jenkins or GitHub and simulate a broken deployment caused by a wrong image tag. If you found this video helpful, hit like, share and subscribe so you don't miss the next video. Thank you for watching and see you in the next video. You just set up CI/CD with GitHub Actions. The workflow builds fine, but when it tries to push Docker image, we see access denied, push failed, CI/CD broken. This mistake happens in real pipelines all the time. Today, I'll show you how to fix it and build a fully working GitHub Actions workflow for Docker. If you are new here, hit subscribe right now. Every week, I don't just explain DevOps tools, I break and debug them, just like you'll have to in production environment. By the end of this video, you'll have a pipeline you can use in your own projects. Alright, let's get started. First of all, let me give you a small explanation about what exactly we are going to do. This is my GitHub repository. In this GitHub repository, we are going to write YAML file, that is nothing but our GitHub Actions file. In this file, we are going to build Docker image. Okay, followed by we are going to push this Docker image to Docker Hub registry. From this registry, we are going to pull that image and run it on our local machine. Also, if this image is public, anyone in the world can pull this on their machine and run the container. Let's jump into our demo. This is episode 9. So I have .github folder, workflows, docker.yaml file, which I'm going to explain in a moment. Application.py. This is once again a very simple Flask application which we were using in all our episodes. Here I am trying to say hello from Flask running via GitHub Actions. That's it. Followed by we have a Dockerfile. It's the same exact Dockerfile which we used in our previous episodes, from Python, creating the user, work directory, copy requirement.txt, pip install, then copy once again and use particular user, application user, expose 5000, command. We are going to run this command. Then we have requirements.txt file. Now let's jump into our docker.yaml file. So what exactly we have here? First, I'm going to name it as docker build and push. Okay, on every push to the main branch. Okay, I'm not creating different branches. I just want to show this. In production environment, you are going to use main branch. So I'm showing there directly. Jobs, build, followed by it is going to run on Ubuntu latest virtual machine. Environment here is, let's say, prod environment. The steps. First, we are checking out the source code, followed by we are using the market actions checkout at version 3. This is, let's say, publicly available. The next step is log into Docker Hub. Here once again I am using a login action with username, secrets.docker username, password, secrets.docker password. This is very, very important. We are going to create this in our Docker Hub as well. Here, this is our docker build command, the same which we were doing locally, docker build -t flask application latest space dot, followed by pushing the image, docker push command. Okay, now our workflow YAML is like ready. I'm going to push this. Now let's jump back to our browser. In my browser, I'm using Docker. I used my credentials to log into Docker Hub. Here I'm going to click on account settings. In the account settings, you will see the settings option, email, password, personal access token. We are going to generate a new token from here. I am saying generate new token. This is for episode 9 demo. Expiration date, I am going to make it as custom. So for example, I'm going to make it expire tomorrow. So I would say at 10 o'clock. Here we have different permissions: read only, read write, delete. Normally read write is fine. Read write delete would be like the best for our scenario. So I'm giving read write delete. After creating this, I'm going to copy these credentials, copy this separately and paste it aside so that it will be easier for us to use that in our pipeline. And also copy this, followed by I'm jumping back to my repository. This is my GitHub repository. I did push my source code already here. So here, if you look at the settings, I'm going to click on settings, scroll down, under security, secrets and variables. Okay, open this, click on actions. In actions, I'm going to say manage environments. Click on new environment, production. Okay, configure environment. Add environment secrets. In the first stage, it would be I'm going to jump back to my Visual Studio Code and copy the Docker username so that I will not make any mistakes. Docker username. Username would be our username, which we copied from our Docker Hub. So it's LearnwithDevOpsEngineer. Add secret. Add another environment variable. And let me jump back once again to Visual Studio Code. copy the password, paste it here. Followed by, we are going to copy the secret value, which we copied from our Docker Hub. Okay, add this secret. Why I'm not typing this? Because manual mistakes are 100%. That's why it is better we copy and paste directly so that we will not see any surprises in our pipeline. Okay, this is done. Now let's jump back to our pipeline. I'm going to push. I did a small change, update file, commit, and sync changes. As soon as we push, our pipeline should start here. I'm going to click on action. Yes, it's queued, as you can see. Update file, I'm going to open this. If you see, our checkout job is running. Setup job is done. Checkout code, login is also successful. Trying to build the image now. And we see the error. Denied request access to the resource is denied. Let's jump back to our Visual Studio Code. Here, if you see, we are trying to build the image, followed by we are trying to push it. Where are we pushing? So we need to pass our username as well. Okay, I'm going to copy this, and followed by I would like to paste it here as well. Slash, then at push step as well. Okay, so that this particular image knows where to push. So this particular username will get injected from our environment variables which we created, safe and secure. Now let's try to push it. Update Docker YAML file, commit, and then sync changes. Let's see if our pipeline will pass now. Actions, it's running now. Building, build Docker image. Now if you see, it's trying to prepare, and also if you see, it is hiding our user credentials. Latest pushed successfully. Now our build is successful. You can see green build, and also if I expand here, it clearly shows that our Docker image got pushed successfully. Now let's jump back to our Docker Hub. Here I'm going to click on Hub repositories, and if you look here, Learn with DevOps Engineer 1 minute ago. It got pushed just now. Now we are going to pull this image locally and try to run on our computer. So for that, I am going to use docker run command, same -p 5000, followed by the username and the Flask application, which we pushed. Press enter. It clearly says unable to find Learn with DevOps Engineer, okay, locally, and it is trying to pull from here. Also, there are some layer already exists. That's not a problem, but overall, it is trying to pull it locally. Now let's jump back to our browser and open localhost 5000. Press enter. If you see, hello from Flask running via GitHub Actions. And just like that, our CI/CD is working end to end. Let's do a quick recap of what we learned today. We built a workflow that builds and pushes Docker images with GitHub Actions. We simulated a real mistake with missing username in the tag. We fixed it by using proper tagging with Docker Hub credentials. Also, if you have noticed, we used latest while building and pushing the Docker image, which is not accepted in production environments. We have to use V1, V2, V3 naming conventions so that it will be very much easy. I'm going to show that in the next episode, and also we spoke about that in previous episodes as well. In the final episode, we'll put everything together, a real production like Docker stack with application, database, load balancer, and monitoring. Don't miss it. Hit like, share, and subscribe so you don't miss the next episode. Thank you for watching, and see you in the next video. Your application just went live. Users are hitting it. Logs are flooding in. CPU is spiking. and suddenly things start slowing down. This is what real production looks like. In this final episode of Docker Home Lab series, we will simulate a mini production environment, Flask application, Postgres database, Nginx load balancer, and live monitoring. Then we'll push traffic, break it, scale it, just like you would do in a real DevOps job. This is the last episode of this Docker Home Lab series. If you missed the earlier ones, go back to episode 1 where we started with Docker versus VMs and follow the whole journey step by step. Hit subscribe right now because by the end of this video, you won't just be running containers, you will be running them like in production. Let me quickly draw today's setup. Users are going to talk to Nginx. From here, it is going to connect to the Flask containers, Flask application. Flask will connect to the Postgres database. Cadvisor on the side. Here's our today's setup. Users are going to hit Nginx. Nginx load balances across multiple Flask containers. Flask connects to the Postgres with persistent storage, and Cadvisor gives us live monitoring what's going on with our containers. This is as close as you can get to production in a home lab. Let's jump into the demo. So I'm going to open my Visual Studio Code. In my Visual Studio Code, I have episode 10, real world simulation, Flask application. In this folder, I have application.py. It's the same exact file which I'm using from previous episodes. Dockerfile is also same. Then we have requirements.txt, .dockerignore, followed by .env file, dockercompose.yaml, nginx.config. So let's look at our dockercompose.yaml file now. First, we are going to start with application, where we are going to build, and it depends on database. Then we are trying to pass some environment variables, db host, db user, password, name using our .env file. Then we are going to expose 5000 so Nginx can reach it internally. We are not publishing here, we are just exposing the ports. Restart unless stopped. Followed by, here comes our second service, database service. Image, environment variables, once again db user, password, db name, volumes, db data, restart policy, once again the same. Then comes our Nginx load balancer. So Nginx image, public entry point port 80, volumes, this particular configuration file we are passing it from here. If you can see, I showed in the previous episode exactly the same file, and depends on application. Restart the same unless stopped. And finally, Cadvisor for monitoring. Here I'm using image from Google Container Registry. Map container port 8080. This means you can access Cadvisor's UI and metrics endpoint at localhost 8080. Followed by, we have volumes. So what exactly these volumes are going to do? First one, mounts the host's root file system read-only. Second, var run gives access to the Docker socket and process info. Sys folder mounts the Linux sysfs kernel data like CPU, memory, stats. Finally, var lib docker mounts Docker's internal storage to inspect container metadata. These mounts give Cadvisor deep visibility into the host and containers. They are required for full metrics, but note that it's privileged access. Then finally, restart policy. Container automatically restarts if it crashes or the host reboots. Now we are going to run our stack with a single command. With a single command, we have our DB, CA Advisor monitoring tool, application, Nginx load balancer. Now we are going to do a small mistake. I'm going to use Docker compose command here and try to pass scale app is equal to 1. So currently only one application is running. We are going to do a load test here using Apache benchmark tool. We are going to run so many requests, 50 concurrent requests at a time at our local host. Press enter. Now let's jump back to our C advisor. It is running fine. I'm going to jump to my Docker containers. In the Docker containers, I can see real world DB1, application 1. I'm going to open this particular container. If you see, we can see some spikes here. So it is coming down, going up, coming down. We are sending so many requests at a time with only one application container. Our servers can't keep up. Requests are slower, CPU spikes as you can see clearly, and logs shows connection delays. This is what happens when you underestimate traffic. Now we are going to scale our containers. Application would be 2 containers instead of 1. Press enter. Followed by we are going to start load testing once again. Press enter. Jump back to our browser. I'm going to go back to my Docker containers. Refresh the page. I can see application 2 once again. So here if you scroll down, Nginx will try to distribute the traffic. We should not see many spikes here. So I cannot see anything here. Let me open another tab and jump back to application 1. So application 1 container. So if you see, it has some spikes, whereas application container 2 doesn't have much. And there it is. Smooth again. Nginx distributes the traffic. Each container takes half the load and our response time drops immediately. That's real world horizontal scaling in action. We can scale more if we are interested. For example, I'm going to run 10 containers here. Press enter so that the traffic gets distributed. Right now I'm seeing some spikes on container 1. So this should go down as soon as we have more containers. So let me refresh this. So application 6. It will take some time, let's say a few seconds to reflect here. This is how we run production like simulation locally on our computer. I'm going to scale down. Once again, I'm going to move back to application 1. That's how you scale up and scale down just by, updating the values on the command line. Let's do a quick recap of this entire episode. We built a production style Docker Compose stack. We overloaded with traffic to simulate failure. We scaled out the application layer to fix it. And we monitored the results in real time. This is the DevOps way of thinking. Don't just run containers, run them like in production. That's it. End of the Docker Home Lab series. From episode 1 to 10, we covered everything from Docker basics to debugging volumes, networking, security, CI/CD, and now a full production simulation. If you followed along, you now understand Docker like a real engineer. Next season, we'll go beyond Docker into Kubernetes and cloud deployments. So hit like, subscribe, and share this playlist with someone who want to master Docker. Thank you for sticking with me for the whole Docker Home Lab series. I'll see you in the next video.